Okay, Ananya, you had a doubt about this question from the quiz. If a plus ib to the power 5 is equal to p plus iq, then you have to find out what b plus ia to the power 5 is equal to. One way which probably most students would go about doing is go ahead and expand. Yeah. So a plus ib whole to the power 5. For this, obviously, you need to know the binomial theorem. You need to know how to expand. Yeah. So I have just expanded it using the binomial theorem. You'll have to wait until we actually do the binomial theorem in math in order to understand this. But assume that you know it and you can proceed with that. Yeah, a plus ib to the power 5. You can simplify. After that, with the knowledge that I squared is equal to minus 1, I cubed is equal to minus I to power 4 is equal to 1, I to power 5 would then be equal to I. Yeah, so I've just used that in the third line here. And then we can group the terms that have I and the terms that do not have I. So here we have the real part, and here we have the imaginary part, and let's call that equation 1. Then we can say, aha, let's do the same with b plus ia to the power 5, exactly the same thing. And we come to this third last line. Yeah, that's what we have. We can see that there's a difference between this line and the line that we had here, the third line here. There are some i's where each term that has an I in this equation up here does not below. Yeah, and vice versa. So suppose we take I out common. Yeah, so that's what I've done in the second last line. Take I out common and see what you get, and then regroup. Yeah, so inside the brackets I've grouped real and imaginary parts. Yeah, so the real part here and the imaginary part here, and we compare that. We say that's equation 2. We compare equation 1 and equation 2, and you can see that the real parts are the inside the bracket in equation 2 is the same as what's up here in equation 1. The imaginary part in equation 2 inside the brackets is the same as this, except we have a minus sign. And then we have an additional I outside. So you have to now interpret what this means. Yeah, you can see that inside the brackets, yeah, we have the conjugate of the right hand side in equation 1. That much at least we know. But what do we do with this I? Now, in order to take into account this I, you will have to resort to polar coordinates and the understanding of what happens when you multiply two complex numbers. Now, if you're going to do that, you might as well start that way itself. Yeah? Another reason why we would start that way is, say, what if I've been given a plus ib to the power 9 or 23 or something like that, a very high degree. There's no way I'm going to be writing all those terms and grouping and all. That makes no sense. Yeah, what does make sense is to work with the polar coordinates. So that's what we're going to do. So here we go. Assume that a plus ib actually can be represented as r e to power I theta. Now you can see that b plus ia will have the same modulus, which means its modulus is r. And let's say the argument instead of theta now is alpha. So this b plus ia is r e to power I alpha. So we can see that the argument of a plus ib is theta, argument of b plus ia is alpha. Automatically we get this. Tan theta would be b by a, and tan alpha is a by b. But a by b is nothing other than cot theta. Okay, and that allows us to say that alpha is actually pi by 2 minus theta. Now, b plus ia is therefore r e to power I pi by 2 minus theta. Okay, now from what we know about a plus ib, let's raise that to the power 5, and since we're dealing with polar coordinates, all we get is r to power 5 e to power I 5 theta. Yeah, because you know that the modulus would be raised to the power 5, the argument would be multiplied by 5. That's exactly what we have here. So we've been given that p plus iq is a plus ib to the power 5, which is r to power 5 e to power I 5 theta. So what that tells us is that the modulus of p plus iq is r to power 5 and its argument is 5 theta. Now let's go to b plus ia. Yeah, b plus ia to the power 5. Yeah, from this relation up here, would be r to the power 5 e to the power I times 5 pi by 2 minus 5 theta, and using allied angles we can see therefore that that comes out to be r to the power 5 e to the power I pi by 2 minus 5 theta. So you can see from this equation therefore that the modulus of b plus ia whole to the power 5 is r to the power 5, and its argument is pi by 2 minus 5 theta. Now we saw earlier that the argument of a plus ib equals to theta automatically gives us that the argument of b plus ia, which we called alpha, that would be equal to pi by 2 minus theta. And we got tan alpha is equal to cot theta. Okay, so using that we can say that the tan of the argument of b plus ia to the power 5 is simply tan of pi by 2 minus 5 theta, which is cot of 5 theta. But from our original what we were given, tan of 5 theta is actually q by p, and therefore cot of 5 theta is p by q. And just to recall, the modulus of b plus ia whole to the power 5 is equal to the modulus of a plus ib whole to the power 5, and that would be square root of p squared plus q squared, which automatically gives us, with these two values, knowing the argument and the modulus of the complex number, that b plus ia whole to the power 5 is q plus ip. Now, this can be used left, right, and center, the polar form of the complex number, and it is a much easier way of getting about things rather than talking about expanding using binomial theorem and all that. So I hope this helps you understand. Yeah.